Good day, class. For this video, I will show you the complex number function of this calculator in order to solve total impedance and total power in the field of electrical engineering. First, we have to set the complex mode of this calculator by simply pressing mode, and we can see 2 for the complex mode of the calculator, and we can verify in this calculator that we are already in the complex mode. Okay? And in order to see the different functions inside this or under this complex number, so we press shift and then 2 for the complex functions. So in this case, for number 1, we have arc function. So arc function is used to get the angle of a complex number. For number 2, so we have conjugate function. So we have to perform conjugate of a complex number. For number 3, we get the polar equivalent of the complex number. So for example, we have rectangular form. We can convert that to its polar form. And for number 4, we get the rectangular equivalent of the complex form. So in particular, if we have a polar form, we can easily convert that into its rectangular form. So in order to understand the function of this calculator, let us solve the problem in the previous video. So in this case, we have the total impedance of the network as seen on these terminals. So we have 3 impedances as solved or as computed in the previous video. So we have here first impedance Z1, capacitive impedance, second impedance or Z2, and the last impedance is Z3. And we already solved the first impedance. The first impedance is 5 plus J3. For the capacitive impedance Z2, this is negative J2.0833 ohms. And for Z3, so we have 2 plus J 3.6 ohms. So again, if you wish to solve for the total impedance of the network, the total impedance is Z3 parallel connected with Z2, and this impedance is later on connected in series with Z1. So using our calculator, we will store Z1 to variable A, Z2 to variable B, and Z3 to variable C using this calculator. So let's start with Z1. So 5 for the real component, and for the complex component, we have 3. And in order to differentiate the real number with the complex number, so we have this function I, so denoting that it represents the complex part or imaginary part, or simply the y-axis of the complex number. So in this case, we have 5 plus 3i, and we store this to variable A. And next, we store the Z2 to variable B, so negative 2.0833, okay? And this is negative J, so we have I there, and store to variable B. And for the last part, so we have 2 plus 3.6i, and we store that to variable C. And in order to get the total impedance, first we consider parallel connection of Z3 and Z2. So that is equal to Z3 is C inverse plus Z2 is B inverse, and get the inverse again for the parallel connection. And for the total impedance, we add the impedance in series, and that is Z1 stored to variable A, and that is equal to 6.377 minus 0.1. So in order to see the whole number or the complete complex number, we can press this button. Okay, the SD button. So this button converts fraction to its decimal equivalent. Okay, and we can see here we have 6.378. So same with this, 6.378 minus J 0.128. So this is now the complex part. And this is now the total impedance of the network. Now, if we wish to convert this impedance from its rectangular equivalent to polar equivalent, all we have to do is to consider answer, and then we convert the answer, the complex form, into its polar equivalent in this case. So we just have to press number 3. Okay? So we are converting the complex number, the answer, final answer, into its polar form. And this is now the polar equivalent. And again, press this button. Okay, 6.379 angle negative 1.151. And the unit for the angle is in terms of degrees as indicated in the mode of our calculator. So that is for the total impedance of the network. And for the total power, let us recall this given. So we have 4 loads of the system, and the power equivalent of each load is summarized in this table. Okay, we have loads 1, 2, 3, and 4. So before we solve this problem, let us first reset the memory. So shift, clear, and then memory clear. Press equal sign, and then we are ready to go. And in this example, for load 1, we store this to variable A, and load 1 is 5,000. Okay, 5,000 minus, so indicating that this load is capacitive. So 5,000, okay, 5,000 I, and store that to variable A. And for load 2, that is 15,000. Okay, no reactive component or no imaginary part, so store this to variable B. And for the third load, so we have 12,000, okay, plus 12,242.4487 I, and store this to variable C. Okay, and for the last component, the real part is 4250 plus 2633.1934 imaginary component or complex part, and store that to D. Okay, so we have 4 loads. In order to get the total power, we just have to get the summation. So A plus B plus C plus D. And for the total power, we press this button, 36,250. So this is the real part, and 98,000 or 9,876 rather, 0.3621 for the imaginary part. So this is now the total power of the system in terms of, in this case, rectangular form. And we convert that into its polar equivalent. So we simply press shift 2 and then press 3 to convert our complex number into its polar equivalent. And this is now the polar equivalent of the complex number or the total power. So we press SD button, okay, and the answer is 37.571 kVA for the magnitude, and for the angle 15.240 degrees. So in this problem, we are interested also in the power factor. And in solving the power factor, we just have to consider theta. 15.241. So in this calculator, so the answer is this power, and we have the complex function shift 2. So we have number 1 function arg. So in order to get the theta in a complex number, so we press 1 for the argument of the answer. So we get the angle that is equal to 15.241. And in order to solve for the power factor, so cosine of answer, that is equal to 0.9648 power factor lagging, as indicated in the problem. So next example, we consider the two motor system. So we have two motors, motor 1 horsepower, and another motor 3/4 horsepower. Okay, and we already solved this problem. For load 1, this is now the summary, real power and reactive power. For load 2, real power and reactive power. So before solving this problem, we have to reset first the memory. Okay, and verify or ensure that the calculator is in complex mode as indicated in the screen. And we store motor 1 to load A or variable A. So we have 828.8889 plus 272.4430 imaginary component or reactive power. We store that to variable A. Okay, so let us verify. So we store the complex number into variable A or load 1 or motor 1. Now we consider motor 2. So 608 1522 plus 177 3777 complex part, and we store that to variable B. And let us verify. So we store this function to variable B. Okay, 608 plus 177.3777, store that to variable B. And we have load A or motor 1 plus load 2 or motor 2. And this is now the total power of the system. And this is in terms of rectangular form. And the answer is the same with the computed values in our slide in the previous video. Okay, and we convert this into its polar equivalent. So all we have to do is to press shift 2, okay, and press 3. We convert the complex number into its polar equivalent, that is equal to, okay, 15 or 1505.7974 angle 17.381, which is also the same with this value. Okay, so this is now the total power of the system. Okay, and next is to solve for the power factor. Okay, but before we do that, let us first store the power, the computed power, into variable C, just in case we needed that later. So variable C in terms of polar form is 1505.797 angle 17.3811 degrees. So if we wish to solve for the power factor, then we get the arg, the argument of variable C, to get the angle, and then cosine of the angle, so that is the power factor, 0.9543 positive, meaning we have lagging power factor. So next is to find for the current. So we have power, okay, the computed power, here is C divided by, okay, the voltage in the system is 230 angle 0. So in terms of polar form, this is 230, and we press shift and this part, okay, for the angle. So 230 angle 0. So C is the computed power and 230 angle 0 is the voltage of the system. So that is equal to this part in terms of rectangular form, but in our solution, we express that in terms of polar form. So in terms of polar form, let us check. Okay, we have here 6.5469 magnitude, and the angle is 17.8311 degrees. So take note, this current is not the final, or this value is not the final value of the current, since we have to perform conjugate. So there is a conjugate function here. So the answer is in terms of current, and in order to perform conjugate, we just press shift 2 and then press 2 for the conjugate of the answer. Okay, currently the computed value of the current, and the answer is this one. So take note, this is in rectangular form. We convert that into polar form. Okay, and in terms of polar form, we press this part. So we have 6.5469. So same magnitude, but take note of the angle. We have negative 17.3811 degrees. So in this problem, we showed the function of getting the angle using arg function, getting the conjugate using conjugate function, and converting polar to rectangular or vice versa. So I hope this video showed some sort of technique, or added your confidence in terms of implementing impedance, power, or in general complex numbers in the field of electrical engineering. So for the other models of the calculator, so there are sometimes different implementations, different syntax. You just have to be familiar with the proper syntax by simply reading the manual of the calculator. So these functions and or syntax is applicable to this particular model. Okay, so that's all for this video, and thank you very much.